Okay, here are the video notes for lesson 3.1, exponential functions and their graphs. Throughout this chapter, we do focus heavily on exponentials and logarithms, and today is going to be our first look at some of that, starting off with just your basic exponential function, which is base a raised to the x, where a has to be greater than 0 and a cannot equal 1, because if a equaled 1, 1 raised to any power is still going to be 1, and so we say greater than 0 but can't equal 1. Let's take a look at just plugging in. So the base here is 2. Let's plug in some x values here. When we do that, this looks like 2 raised to the negative 3.1, which gives me 0.1166, and that's just me plugging that into my calculator. Okay? Please make sure to use parentheses when plugging it into your calculator too. It's going to make sure that they know that that's a negative 3.1. Always use parentheses on that calculator. Okay? Plugging in the next one, this is 2 raised to the negative pi, and that's going to give me an answer when I plug it into my calculator of 0.1133 after I round it. And then the last one here, we have to plug in, we have 0.6, and that's going to be raised to the 3 over 2, or 1.5 if you like decimals. And we have 0.4648 if I round it. Okay? So again, that's just plugging in some kind of exponential into, or some kind of exponent into your function. Now, graphing these functions, we're going to use XY tables. Okay? And so what that looks like is X, Y, and my X's are negative 2, negative 1, 0, 1, and 2. Plugging that in, I would get 2 raised to the negative 2. Well, that's the same thing as 1 over 2 to the positive 2. Remember that rule there, okay? Whenever you have a negative exponent, you can put it in the denominator and get it to be positive, or if it's a negative in the denominator, it'll bring it to the numerator, okay? And so this would turn into 1 over 4. This would turn into, we'd have 2 raised to the negative 1, that becomes 1 over 2 to the positive 1, so that's 1/2. You'd have 2 raised to the 0. Anything raised to the 0 power, anything raised to the 0 power is going to equal 1. So that's 1, and then you have 2 and 4. And so if you graph it, we'll see the graphs down below here. And we'll do this one quick. We have x, y, negative 2, negative 1, 0, 1, and 2. Same kind of thing. 4 raised to the negative 2, that's 1 over 4 to the 2, which is 1/16. This would be 1/4, 1, 4, 16. And you can see how fast that grows in the matter of 4 x values. You can see how quickly it's growing. That's why it's exponential. And taking a look at these graphs here, you can see how much more quickly 4 to the x goes than 2 to the x. Okay? And that's what it says here, increasing more rapidly due to that 4 to the x. Okay? Let's see what happens with a negative exponent here. Same kind of things. XY tables. You have negative 2, negative 1, 0, 1, and 2. But this time you'll have 2 raised to the negative, screw that up, negative 2, which is going to give you 2 raised to the 2, which is 4. And you'd have 2 raised to the negative 1, which is 2 raised to the 1, which gives you 2. So then this is 1. It's going to just be the exact opposite of this one here. Okay? Because if I plug in a positive 1, that's going to be 2 negative positive 1, which is the same thing as 2 to the negative 1, which is 1 over 2. And you can see the connections here. Hopefully you can see the connections between this right here, 4, 2, 1, 1/2, 1/4, 1/2, 1 over 2, 1, 2, 4. So it just flipped it because of that negative x. Okay? Same kind of thing is going to happen with 4 to the negative x. So we have x, y. You have then, it's going to flip this. So my first term is going to be 16, and then it's going to go all the way down. So we're going to have 16, 4, 1, 1/4, 1/16. I'm doing that even before I put my x values in, negative 2, negative 1, 0, 1, and 2. And just for some reassurance that I know I'm right, 4 raised to the negative 2 would give me 4 raised to the positive 2, which is 16, which is what I see here. Okay? And do they have a graph on this one? They do not. The graph would look like, just quickly, for the first one here, we start up at negative 2 up at 4, and we're going to swoop down like this. Okay? Here we have it increasing a little bit more, and so if we graph this one, we have negative 2 here, up all the way at 16, and then we're going to swoop down as well. These are rough sketches. These are rough sketches here. I should probably plot all the points, but for time I am not, because I believe in us being able to plot points and sketch these if we need to. Okay, the domain and range of your basic characteristics, this one is in your notes, so make sure you take a look at those written notes and write in here. Okay, same goes for the negative x. Take a look at the written notes, write in domain and range in your y-intercept, and so I don't have to take the time here to do it. Couple big notes too. Again, this can be looked at in the written notes, but these are always going to pass the horizontal line test, which means they are one-to-one functions and have inverses. So, and we see here, we have b is going to move it up or down, c is going to move it left or right, negative a is going to reflect over the x, negative x is going to reflect it over the y, and we did see that already. We saw that reflection over the y here. So it went this way when it was a positive x, and reflected over the y here when it was a negative x. So we saw some of that. And make sure, again, you're taking a look at those written notes to see those right there. And then let's talk about how these are going to move. So the first one here, it's just like if we had a to the x plus 1 in parentheses there. This is the same kind of thing with the plus 1. This is going to go to the left. When it's attached here, this is a good one. When it's attached, that c here is going to move it left or right, and when it's a positive c, it moves it to the left in this case. So that's left 1. This is down 2. This is a reflect over the x-axis because we have the negative a, so we have that in that third case, and then we have a reflect over the y-axis here in the last one. Here's the one-to-one property, and all they're saying here is if you have the same base. If it's a to the x, so the base is a, and then you have another one, base a to the y, you're allowed to set x equal to y. And so what that looks like here is we have 9 equals 3 to the x plus 1. Well, 9 can be rewritten. 9 can be written as 3 to the second power equals 3x plus 1. Now we have the same base, and so we're allowed to set the exponents equal to each other. And so we can say that 2 equals x plus 1, which we solve here and get 1 equals x as our answer. Here we can flip this, so this becomes 2 to the negative 1 raised to the x, because that's like 2 over the positive 1 here, and when it flips up, it becomes negative. That's where that 2 to the negative 1 is coming from. And then this becomes, because when you have an exponent raised to another exponent, you're allowed to multiply, so this becomes 2 to the negative x, which equals 8. You could rewrite it so it's 2 to the negative x equals 2 to the third power, because 8 is the same thing as 2 to the third power. Same base, we can set them equal to each other. Negative x equals 3, which means x equals negative 3. And that would be your answer there. Keep moving along. That's the one-to-one property. We have one more here where we introduce e, and it's the same kind of thing. You're allowed to set these equal to each other. All right, and I'm not going to do this example because I don't really need to. You would set them equal to each other, and then you would actually end up being able to factor that and solve for x that way. Here's an introduction to the natural base e. E is just a constant, and we'll learn more about it when we talk logarithms, but e is just your constant. It's 2.17 irrational number repeating. All right, and when you see e to the x, it's a pretty common exponential function used in the real world quite a bit, and we'll see that at the end. Okay, so here is where we would plug in a bunch of different numbers into our function, but I'm going to skip over that so I can get to what I want, which is our compound interest and our continuous interest. Okay, and so here we have P is going to be our principal, kind of our starting money. Make sure I spell that right. I think it's principal like that. And then we have N being the number of compounds. So, you know, if it compounds quarterly, if it compounds monthly, if it compounds every 3 months, whatever it might be, all right, that's going to be our number of compounds. R is our rate, or our interest rate. And time, or T is time in years. Okay? We also have, that's compound, that was compound interest. This is compound, this is compound, interest, and this is compound continuously, where we get to use APERT. Okay? And APERT, same kind of thing. Principal, E is that E, the natural base here. So P is the principal, E is E, R is still the interest rate, and T is time. And so let's look at here a problem where we get to work with compound continuously and just compound interest in terms of quarterly and monthly. Okay? For quarterly, we're going to use N equal to 4 because there's 4 quarters in a year. And so my number of compounds, my N, is going to be 4. My principal is 12,000 from right here. I have an interest rate in R equal to 0.09 from the 9% here. And I have a T that is equal to 5 from 5 years. Okay? And so if I set up using my equation here, I have 12,000. Sorry, I gotta look at what we have. We have A equals 12,000 times 1 plus your rate over your number of compounds. And so that is 0.09 over 4. And that's going to be raised to the N times T, which is, for us, 4 times 5. Okay, now it just becomes calculator work. Okay, I'm going to start with the things in the parentheses first, and I'm actually going to pause and work through it for the sake of time and come up with my answer. What I end up getting was 18,726.11. Okay, and that's just using my calculator. I did the division here first, added it to 1, raised it to the power of 20, and then multiplied at the end by 12,000, and that's just using order of operations. Parentheses, exponents, multiplication. Okay, monthly, we have things kind of change. The only thing that's really going to change is N is now going to be 12 because there's 12 months in a year. And so it becomes A equals 12,000 times 1 plus 0.09 over 4 raised to the 4 times 5. And again, I'm going to pause and do the calculator work. Sorry, I screwed this up. I got to erase it. This is not 4 and this is not 4 because that was from the last one. This is now 12 and this is now 12. And now I'm going to do my calculator work. What I end up getting as an answer was A equals 18,788.17. And then compound continuously, that's the APERT. And that's raised to the RT, sorry. APERT like this. And we have principal. This time we don't really have to worry about an N. We have A equals 12,000 times E raised to the rate, which is 0.09 times 5. And again, calculator work here to end it. I came up with an answer of A equals 18,819.75. And that would be continuously. All right, I am running out of time here. The homework is going to be updated on Google Classroom, so make sure you look for that. And any questions about any of this, please let me know.